All right, we're at the end of chapter 3 about computer arithmetic. If you remember, the last thing that we did was to recognize that we can take the algorithm for floating point addition and turn it into hardware. And so what I want you to see in this slide is that we've actually got step 1, step 2, step 3, step 4 with a loop. This is actually the algorithm, and the steps in the algorithm are compare, shift right, add, normalize, and round. And the hardware to do those steps is shown in a kind of a top-to-bottom flow structure. So it means that you can do complicated algorithms in hardware as long as you know the tools to use. And you can see the building blocks are ALUs, multiplexers, shifters, normal things that we learned about in CS-224. Okay, so this is for floating point adder. Let's move now to floating point multiplication. I think we all recognize, don't you, in multiplication, we multiply the two fractional parts and we add the exponents. So there's no need for the exponents to be the same. We don't have to compare them, find out which one is bigger. So there'll be similarities. We're going to use a multiplier now for the significands and not an adder. If you step back one, here we're actually adding the significands. Now we're going to need to multiply the significands. And so that'll be different. And floating point arithmetic hardware will do addition, as shown on the previous slide, subtraction, which is essentially the same as the previous slide, multiplication and division, which the book talks a little bit about, reciprocal, square root, those kind of things. These are typical operations required in floating point mathematics and floating point numbers. And of course, you want to build them into hardware to make them fast. So this is the kind of hardware typically that processors include for floating point mathematics. They also include an interesting one where you can convert an integer into a floating point number or a floating point number into an integer. And that's a nice one to think about how to do that as well. Obviously, the fractional part simply has to be rounded. We have to turn it into the nearest integer. And operations usually take several cycles in floating point because we don't want to stretch out the clock and have a very slow, long clock to get everything done in one clock cycle. So we pipeline the operations. We divide, for example, if I go back one slide, if this is a long delay from here to here, we'd say, oh, that's too slow. I mean, it's obviously all combinational. You can see that. But what we would do is pipeline it. We'd probably have a register that catches those results there, and maybe one that catches there, maybe one that catches there. So we do it in 3 or 4 clock cycles. Typically, pipelining is done to speed up keep the clock fast. And so then floating point mathematics becomes a multi-cycle operation. Integer addition, subtraction, multiplication, division can perhaps be done in 1 clock cycle, but certainly not floating point. So that's something to remember as well. All right, now let's move from hardware to the instructions offered at the machine level so that we can see right at the interface between the hardware and the software what is made available in the languages of these processors that have floating point support, which these days are all processors. It's impossible to imagine a processor that wouldn't have floating point support except a very tiny embedded 8-bit processor. Okay, the first thing is that in the old days, when there weren't enough transistors, the floating point units were put into what were called coprocessors. So you'd have the main processor, which included as many functions as you could get into the amount of transistors back then. And before Moore's law gave us something like that, the coprocessor had to do the floating point work, and it was a separate chip. So the phrase coprocessor still exists. And so in MIPS, the floating point hardware is called coprocessor 1. Now, it's merged together, of course, but the instructions will have coprocessor 1 in them. And you could consider it an adjunct processor that extends the ISA, because you have an ISA already with integer math, and now we're extending it, you might say, with floating point. Okay? We're going to have separate floating point registers because the ability to have integer registers that hold integer values and floating point registers which hold floating point values doubles our number of registers, and it keeps us from having conflicts and will enable the processing to be faster by having a parallel set of floating point registers. So these are 32 registers, and they have numbers F0, F1, all the way up to F31. They hold single precision floating point numbers. Well, what if you want to have a double precision number? then you take two of them and pair them. And the highest 32 bits will be here, and the lowest 32 bits will be here, and now you have a 64-bit value stored over two registers. You pair them for double precision, as we said. Now, release 2 of the MIPS ISA supports 32 64-bit floating point registers as opposed to 32 32-bit floating point registers. So we actually now, because if you pair them and only have 31, then you really have 16 registers for double precision math. So the second release ended up with 32 registers for double precision math. The floating point instructions only operate on the floating point registers. Integer instructions only operate on the integer registers. That seems clear enough and fair enough. Programs generally don't do integer operations on floating point data or vice versa, so it fits the need anyway of the way programs operate. And this gives us more registers, and therefore that's going to keep the code size minimum because we don't, we'll still have 32, so the number of bits is 5, so the 5-bit field in the instruction formats doesn't have to change. We didn't add registers to the general set, we just kept two separate sets, each of which can be specified with a 5-bit register address. Now, we have to do loads and stores for those registers, which are different than the loads and stores for the integer registers. So we come up with a load word into coprocessor 1, load, I forget, D into coprocessor 1, store word into double. Load a double into coprocessor 1, store a word from coprocessor 1, store a double from coprocessor 1. Okay? And so here would be an example. Load a double into coprocessor 1, into register F8, and of course F9 as well. So that's the double. From where? From memory. Starting at what address? 32 up from the stack pointer. And how many bytes will I transfer in that instruction? From memory into the register? How many bytes? 8 bytes, because it's a double precision 2-register word. So I'm going to get not 4 bytes, but 8 bytes. So the next 8 bytes from this location will come into F8 and F9. Okay, and that'll be the double load. Yeah. The doubles all start with an even number. The doubles start with 0 or 2 or 4, so 30 will be the last beginning for a double. We can't start with 31 for a double. You can do a single precision load into 31, but not a double. Yes?
So can we store exceptions for if you use F9, for example, for doubles?
Either it throws an exception, or frankly, yeah, if F9 ends up somehow in the assembly language code and in the machine code, and it wasn't caught by the compiler or the assembler, which it should be because it's obviously, but somehow let's say you had 8 and it changed somehow in memory error to 9, and you actually fetch it and you decode it and it's a wrong value, it's an odd beginner, yes, it should throw an exception. It should say, I've got a bad instruction here, you're asking me to do something I don't know how to do in hardware, therefore I stop. Yeah, that's exactly right. Kind of like an arithmetic overflow, actually. Okay, let's continue with the MIPS instructions to support floating point math. Okay, so now we're going to have add, subtract, multiply, and divide instructions, but they can be single precision or double precision. So when they're single precision, we put .s. So this is a single precision add of two values, which are in the floating point registers that are each 32-bit, like add.s of these two, put the result here. And then, of course, double precision arithmetic, add, subtract, multiply, divide, .d, those are going to use two registers to do the job. So F4 and F5 is one of the sources. F6 and F7 is the other source. You're going to multiply them together, double precision, and the result is going to go into F4 and F5. Okay, everybody see how that works? Okay, again, we begin the doubles on even-numbered registers. Okay, now you can have comparisons. You can compare two floating point values. This is often done. So compare .xx single precision or compare .xx double precision, where xx is it equal, is it less than or equal? Ah, look here, we have a compare. We didn't have compare before in integer. What did we have instead? Just direct branch. Branch if equal or branch if not equal. What are we doing here? First, we're comparing with all 6 possibilities. Equal, not equal, less than or equal, greater than or equal. We first compare, and then we're going to do our branching after that. Ah, we slowed it down, didn't we? Yeah, okay. But now we have all 6. Why did we give all 6 in floating point comparisons, but not give all 6 as, built-in instructions in the machine in the integer? Why give all 6 possibilities here? Equal, not equal, less than. We built it in kind of a weird way in the integer comparisons. Yeah, you can do the other 4, but it takes 2 instructions. Here, we're saying no, they're all equal.
If we had 6 instructions here, we slow down the integer common case.
Yes, the integer comparisons, a large percentage of them are either equal or not equal. The others are the uncommon case. What does this tell you here? In floating point math, we use them all more or less equally, so there isn't any common or uncommon case. They're all roughly equally common. That says something about what integer arithmetic and floating point arithmetic do. They do something different here, okay? And so loop controls are in floating point are very often looking for greater than or equal, less than or equal, things like that. All right, and then after you've done the comparison, now we have branch. And the branch says what? Branch coprocessor 1 if true, branch coprocessor 1 if false. So what are we saying here? We're saying the floating point branch, if it's true, do it. The floating point branch, if it's false, do it. Okay, so we've set the condition here by the comparison. Yes, it is, or no, it isn't. And then we branch on the positive or the negative of the condition that we compared. So all branches are now a 2-step branch. Okay. All right, that's a little bit different too. And now let's look at a little bit of code using floating point arithmetic instructions. A real simple thing here, I don't know if you're aware, but there's 2 temperature measurement systems in the world. There's the centigrade system, which all normal people use, and then there's the weird Fahrenheit system that the British gave to their descendants, including the United States. So when I came to Turkey, this is the only kind of temperature I understood. Yes, in a science course I've heard that water freezes at 0 Celsius and boils at 100, but that's about all I knew. If somebody said, it's 27 outside, I would say, man, get your coat on, it's really cold. And you guys are like going to the beach at 27. So, completely different, okay? Anyway, there needs to be a conversion. And the formula for conversion, if you ever learned it, I don't know if you ever needed Fahrenheit here in Turkey, probably not. But the formula conversion is subtract 32 from the Fahrenheit number, and then now you have a number, because we freeze at 32. Water freezes at 32 and boils at 212. That's weird. But you can tell that for the range between freezing and boiling is 180 degrees, whereas here it's 100 degrees. So that tells you, oh, each degree is 5/9. Each Fahrenheit degree is 5/9 of a Celsius degree. Anyway, so the formula for conversion needs this. So what do we need? A floating point division, a floating point subtraction, and a floating point multiplication. We got 3 floating point operations to do this. So let's see how it works in MIPS code. Load the constant 5, which is a floating point constant. Where is it? It's pointed to by the global pointer. It's in the global data. So we're assuming that 5.0 as a floating point number is stored. Bring it in and put it in F16. Okay, using load word from coprocessor 1. Bring in the 9 and put it in F18. So now I've got the 5.0 in floating point and the 9.0 in floating point. And now I can do a single precision division of 16 and 18 and put the result in 16. Can you tell me what would happen if I did integer 5 divided by integer 9? 0 with the remainder of 5. That's not going to be very helpful, is it? You need floating point numbers if you want to get what this really is and then multiply it. So integer division is pretty much useless. We need floating point to get, useful numbers. Okay, so now we've done the division, and we've got this one here in F16. Now we need to do a subtraction of 32 from the Fahrenheit. So we're going to bring in the constant 32 from wherever it was stored in the static part of memory and put it in F18. And Fahrenheit is supposed to be in F12. So now we can do a single precision subtraction from F12, subtract F18, put the result in F18. So this is in F18, and this is in F16, and now it's time to multiply them together. So we do a single precision multiplication on the F16 and F18 values, and put the result in F0, and now JRRA. Okay? So that's the conversion code. Any questions about that? Single precision floating point. Now, what would happen if I wanted to do double precision? Double, 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 double. What would I do? How would it change? Well, D, D, D for the 3 operations. That's great. What about this? What did that do? That brought in a 32-bit number and put it in F16. Yeah, somehow I need to get the rest of it and put it in F17 if it's a 64-bit number. So I'm going to need 2 of these to bring in a 64-bit number, and 2 of these to bring in a 64-bit number, and 2 of these, right? I'm going to need LWC1 twice to get both halves of it, right? Because this load brings in 4 bytes and sticks it in a register. So I need, therefore, to bring in 8 bytes to stick it in 2 registers. So therefore, that's how it would change. These S's would be D's. That would be 2, 2, and 2. Okay? All right, any questions about the math here? There's a more complicated example in the textbook, including, it involves arrays. But I'm going to let you study that. It's at the end of the chapter, and it's actually some really good code using double precision math. And it involves 3 nested loops and how to do array indexing and calculation, including a product added into a sum inside 3 nested loops. So that's pretty good code. I just want to recommend that you study that and work through that so that you will really understand serious floating point arithmetic at the low level. I'm going to finish up our lecture and give you some time to talk in your groups and begin your design review. Okay? So we're going to finish up by talking about something that's kind of strange and not very intuitive. It's associativity. Do you know what associativity is? If you remember, it says A plus B done first and then C later gives the same result as B plus C done first and then A added later. The order of addition and multiplication doesn't matter. But we all know that the order of subtraction and division does matter. So what do we say? We say that in arithmetic, addition and multiplication are associative operations, or they obey the associative property, or we even talk about the associative property of addition, the associative property of multiplication, but we don't talk about it for subtraction and division. Okay, so that's what we understand from our theory of math. I hope that, I don't know what you call it in Turkish. Does anybody know the name for that in Turkish? There's 3 properties that you learned, I'm sure. The one is, it doesn't matter the order, you can commute them. That's called the commutative property, change places. One of them is about the grouping, that's this one here, the order of operations done. The first one's about order of operands, that's called commutative. What's the... Okay, the second one is about order of operations, and that's the associative. And then the third one is the distributive property of multiplication over addition, right? So there's 3 properties, commutative, associative, and distributive. And they must have names somewhere along the way in your math theory you learn them. All right, this is talking about the associative property. Okay? All right, so you got to fix, that's a reference point. Now, let me shock you and tell you that floating point arithmetic in computers is not associative. Floating point arithmetic in computers is not associative. Watch why. Okay, I got 3 values, x, y, and z. Let's let x be an extremely small negative value, and y be exactly the same extremely, no, these are large, extremely large positive value, and let z be 1. Okay? All right. So now, if I do x plus y, adding those together, everyone can see it's going to give us 0. And then z later, 0 plus 1 gives 1. So the answer is 1. And that's the correct answer, in fact. Now watch what happens in limited precision floating point math in computers. If I do y plus z first, that says add these 2. Well, this is e to the 0, and this is e to the 38. And you can imagine that when I add this little bitty 1 to this enormous number, you know what's going to happen? It gets rounded off. It can't, we don't have the precision to represent it. So the answer of that is this. This plus this equals this. Why? Because the computer doesn't have the accuracy and the number of bits to hold something that's 38 orders of magnitude in base 10, Barak base 2. That's to be 100 orders of magnitude apart in base 2, at least. Right? 3.1, 110, 120. So therefore, the sum of those 2 is this. And then when I add the x, I get 0. So I get 2 different answers. It is not associative. Theoretically, yes, but practically in the machine, no. Huh. Because of what? You might say, well, because of rounding, or because of accuracy errors, because of limited precision. You can give a name for the problem, but I think we all understand the problem. As soon as you say this plus this in the machine equals that, then you realize we're going to allow a tolerance for errors. The tolerance for errors means we can get different answers. Huh. That means that when you run your floating point math, what you'd like to do, and this is in a course called numeric analysis, is you want to avoid doing these kind of operations. You want to prefer doing these kind. Can you see why? Because when the orders of magnitude are similar, the numbers can be effectively added, subtracted, multiplied, or divided without too much error. When the orders of magnitude are hugely different, then there will be error, and you will lose accuracy in your calculation. Okay? All right, that's just a key point about any real computer arithmetic in floating point. Yeah.
We always lose a little accuracy there because suppose that x didn't have the negative value of y. Those two will give large numbers, and we will still lose accuracy. And if we apply accuracy associativity, I can say associativity, then we'll still lose we'll still have to round up, and we'll end up with the same value.
Yeah, if this is positive, then they both give the same answer, which is 3.0 times e to the 38. That's correct, if this is positive. So sometimes they give associativity errors, and sometimes they don't. And it depends upon the values of the numbers, you see. I'm not claiming that always you get errors. What I'm claiming is sometimes you can get errors, and those errors can depend on the order of the operations. This is a very serious problem, because it means that if you want accurate analysis of global warming, if you want accurate modeling of a nuclear power plant meltdown, if you want accurate modeling of population migrations or sea current flows in the oceans, if you want accurate modeling of a rocket going to hopefully hit the enemy and not your own troops, you better make sure that you think about this. That's my point. Yeah, you have to take it into account. Okay, so assumptions of associativity may fail because floating point operations are not associative. Just remember that. Floating point operations are not associative. Just, here's a proof example. And we need to validate parallel programs under varying degrees of parallelism, because think about this. If I had a parallel program and I distributed it over 8 processors, that could give a very different result than if I distributed over 4 processors. Because which operations will be combined and how they'll be put together, the order would vary, wouldn't it? And so the number of cores available to take your algorithm and run it on might vary according to what other load on the machine is even. This time it took your algorithm, you said parallelize it and use as many cores as are available. We had 4 this time, we had 6 this time, we had 8 next time, we had only 2 the last time. You get 4 different results. Varying degrees of parallelism can lead to this effect showing up. Whoa, 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 okay. Just wanted you to know that there are such little demons hiding inside computer arithmetic, and so you won't be surprised. Don't be soft. Don't be soft. Don't be ignorant that these exist, okay? All right, now, let's talk about support for accurate arithmetic, okay? We want as much accuracy as we can, and obviously there's some cases where it won't matter. You would need to have dozens of extra bits in order to include the 1 when the other number was so large. But the best that we can do is specified in the IEEE 754 standard, again for floating point, and it's for rounding. Floating point numbers need to be rounded. Integer numbers never need to be rounded. But rounded means take the answer and fit it into the number of bits that I have. YA32, YA64. So we've got to fit it. And there's 4 rounding modes that are given. Always round up, which means no matter what it is, we round it toward positive infinity. Always round down. No matter what we're chopping off, we chop off and move toward negative infinity. That means that positive numbers move towards 0 and negative numbers move away from 0. Everything moves towards negative infinity. First, when everything moves toward positive infinity. They're moving in opposite directions. The positive numbers are moving towards 0, but the negative numbers are moving away from 0, not toward it. Or you could always truncate, which rounds everything towards 0. Or the most popular one is round to the nearest even. Doesn't mean the nearest even integer, it means the nearest even in the least significant bit. Okay? Now we're going to have 3 extra bits called the guard bit, the round bit, and the sticky bit. So in reality, in the mathematics, we're not going to be working with 32-bit numbers or 23-bit significands. We're going to be working with 26-bit significands. Add a guard, add a round, and add a sticky bit. Okay? So we've got extra bits, and then when it's time to get the result into the 23-bit significand, we'll have to do rounding, and we can round in any of these 4. Except for truncation, which is easy. This is always easy. Just throw it away. You need some extra hardware, and the hardware has to include extra bits. So in fact, a 23-bit adder or a 23-bit multiplier is not enough. We've got to have extra bits and keep them, and then round off later at the end of our calculation. The guard bit is used to provide 1 extra floating point bit, or F in the, the fractional part, when you're shifting left, because when we shift left, we're bringing in something, and we better have something good, or we'll have to put in a 0 and lose accuracy. So when you shift left to normalize a result, remember you're moving things that way, so you're bringing in to the least significant place. If you don't have anything to bring in, you're forced to write a 0. That's definitely a big inaccuracy. But extra bits allow you to bring in something that's meaningful. That's the guard bit. And of course, we know we're going to have sometimes to shift left if we have to normalize. The rounding bit is used to improve rounding accuracy. So not only do we shift, but now we have an extra round bit. The guard bit came in, but now the rounding bit can help us to know when I cut off, should the guard bit go up or go down? In other words, do I have enough that's greater than half to boost it up, or is it less than half to drop it down? And finally, the sticky bit is used to support this rounding bit if I choose the mode round to the nearest even. So I actually need 2 bits here to decide how I'm going to round this bit. This is the LSB. Let me see if I can draw it on the board. So I had my number. I needed to shift it to normalize it. So I need to bring in the guard bit. So the guard bit now came into the number, and next to the guard was the round bit and the sticky bit. So now the round is here, and the sticky is here. Okay? So we've got a 23-bit number. Now we're going to round it. Well, obviously the round bit tells me what I should do to this, and that'll work for always round up and always round down. But if I choose round to the nearest even, I actually need 2 bits here in order to know what to do with this. Okay? So that's the point of them. You can read about it in the book, but you can see what's going on here. One point, the 23 or the 52 bits of the fractional part, and then GRS must be kept in the hardware and actually computed in the additions, the multiplications, the subtractions, the divisions, the square roots, the inversions. All the floating point operations need to have those extra bits so that when you get to rounding mode at the end, you say, great, there's my final number. It's as accurate as it can be. As accurate as it can be. Okay, are there questions about this? All right, again, I'll just refer you to the textbook. There's a lot in the text that will help you to further understand it, including some examples if you would take the time to do that. And that's the end of our time in Chapter 3.